thank you very much for inviting me to speak. This is a real pleasure. I always enjoy talking about the technology, so so thank you for that. A lot has happened. The evolution of design since I founded the company back in 2007. It's been a remarkable adventure. I'm still enjoying myself very much in terms of the work that we're doing here at NuScale. The evolution of design. Well, the design started, as you mentioned, as a work that we did for the U.S. Department of Energy through the Oregon State University. So I was a professor there, head of the nuclear engineering department for many years, and then later on started the company NuScale Power. Evolution of changes. Started the company with 3 patents. And over the years, we now have 700 patents, either pending or granted in 21 countries. So a lot of innovation happening. About 40% of our company are in their 20s and 30s. So a lot of energy, a lot of innovation that's happening right now. The big changes over time, we started off with a 50 megawatt reactor that was approved by the U.S. Nuclear Regulatory Commission. Now we're at 77 megawatts of power per module, and that's also now been approved by the regulator. So we're the only SMR in the U.S. that has NRC approval, and that's a big step forward. We've also improved our operations, about $2 billion invested in NuScale so far. So if you look at how that money's been used, it's been used to de-risk the technology. On the regulatory side, to de-risk the licensing approach, now that we have the design approval. On the technical side, all the different features of the design that needed to be tested have been tested. So the manufacturing of our steam generator tubes, the vessels, all that is being done right now by Doosan in Changwon. So very nice cooperation there. So we're excited about our partners there. Other areas that we've been working on, of course, the control room, which we're here today, you get to see. So being able to control 12 reactors from one control room was a major advancement for nuclear power. We can do it because of a very new and high level of safety that's being offered by this very simple design. Design engineering is challenging to begin with. The goal, our philosophy, is to design with safety and simplicity in mind. And the challenge, of course, is that you want to add functionality and safety to your design, but at the same time you want to keep it elegantly simple. So simplicity is key to a successful design, and we've done that. I'm very proud of our design teams and what we've accomplished with our integrated reactor, and it's a very, very different approach to technology there. The first step in our design process was we made a decision very early. We decided that we would, wherever we could, we would use commercially available components. We wanted to leverage the existing nuclear supply chain. So that was one of the big things that we focused on. So control rods, fuel, the materials, our water chemistry. We wanted to use existing technology and components wherever we could. But there were some very novel features which make the NuScale design unique. The first one is that we use natural circulation. So we've eliminated reactor coolant pumps. So in the large conventional reactors, you'll have 2 or 4 of these very large reactor coolant pumps, each one using about 6,000 horsepower, so about 4 to 5 megawatts of electricity being used to drive those pumps. We've eliminated all those pumps. So now we have natural circulation. So one of our challenges was to demonstrate that we can get very high efficiency with our system using just natural circulation. By natural circulation, you have a high temperature in the reactor region, a lower temperature above it, and you get a natural convection flow. So no pumps. But we had to demonstrate that not only with our helical coil steam generator, but also with our fuel to demonstrate that we can get the same kinds of energy efficiency that you get with a large plant, but we wouldn't use any pumps. So that was one of the big breakthroughs for us in terms of moving the technology forward. And after we did about $100 million worth of testing on all of our systems, we found that we can upgrade the power from the 55 megawatts, from 50 megawatts to 77 megawatts. And so that's what allowed us to do that, was a very carefully and controlled process of testing and then and design changes. Yeah, I think that the fact that it's a smaller package, that's factory manufactured. So our modules, which include the reactor vessel and all the internals, everything you need to produce steam is in the reactor vessel. And then that sits inside of a containment vessel. So instead of the large concrete containment domes that you're familiar with the conventional reactors, we've eliminated that and gone to a very small steel containment, which houses our reactor. All that is done in the factory. So that's a big advantage because now it's a very controlled environment, and all your nuclear quality materials are being manufactured in a very controlled setting, as opposed to outside in the weather and bad climate. So that's one part of it. The second part is that you can do this in parallel. So now while you're doing your civil construction at the site, in parallel you're doing your manufacturing of the modules in a factory. And then when the site is done and ready to receive modules, you can ship the modules and install them. So it becomes an installation process rather than a construction process. The big advantage there is that instead of a 7-year build, you can build it in 36 months. So because you're not doing your nuclear construction on the site, it's all done in a factory. So that's a very big advantage. The second big advantage, I think, in terms of the scale of what we're doing, is the fact that the plant would always run. So you have, in our 12-module plant, what you have is an opportunity to refuel one module at a time, while the remaining 11 modules continue to produce power. So the plant never shuts down, which means you only need to replace 77 megawatts at any one time, lower replacement costs, higher capacity factors, and that's something that we've worked on very carefully, and we've been able to demonstrate that process here in our simulator. So it's a very helpful approach. It helps the industry as a whole to be more economic and more flexible. In terms of flexibility, what's different about our design is that you have 12 modules, for example. Or you can have 6 or 4, whatever you need. But each module could be used for a different purpose or sets of modules. So we've talked a lot to countries that need desalination. They need clean water. And that's a big issue. So you can assign 2 modules to produce clean water. One module, working with the Doosan's system for reverse osmosis, could produce about 150 million gallons of clean water per day. Significant. So that's enough for a large city. But then you can have 2 modules producing electricity, 2 modules producing high temperature steam for different chemical processes. It's a very flexible design that allows you to have multi-purposes, and each one then could be adjusted to that particular region of the country. And lastly, of course, is that you can add modules as modules are needed. So scalability is a big part of the design, and that was deliberate because not everyone wants 1,000 megawatts all at once. They may want 300, 400, but you can add modules as modules are needed. Significant benefits there because of the flexibility. And I've always emphasized scalability because of that. You can't take a large conventional nuclear power plant and shrink it down and assume that you'll get the same economic benefits. It doesn't work. There is an economy of scale that happens. We have an economy of simplicity and numbering up. So that allows us to be economically competitive. Data centers are very interesting. 4 or 5 years ago, we talked to data centers, and they said, well, we need 100 megawatts, 200 megawatts. And now they're all saying, we need 1,000 megawatts, we need 2,000 megawatts. So there's a huge amount of demand. What we found when we talked to data centers is that they don't want to own or operate a nuclear power plant. And that's always been a barrier. Well, we've entered into this exclusive agreement with ENTRA1. So ENTRA1 is our developer. They finance the plants. They bring together a team of experts, engineering, procurement, construction experts, operators, working with NuScale to build the plant. And then they'll actually operate and can own the plant. So in fact, the data center or the petrochemical company does not need to own that plant. They just sign a power purchase agreement, and then they get the power or the steam or whatever they need from the plant. So it's a very different model. So we're very excited about the innovation that's not just happening in the technology, but also the innovation that's happening in how we finance and build nuclear power plants. Yeah, that's something that we've studied quite a bit. We did our first hydrogen study back in 2013, I think it was, when we first published the study. We did that with Idaho National Laboratory, and the result was very good. Coupling a small modular reactor with high temperature steam electrolysis systems would yield significant amount of hydrogen. So as we talk to different petrochemical companies, we hear we need 250 to 500 metric tons of hydrogen per day, every day. And we need a reliable source of power. And we can't do it with renewables. We need something that's steady, and we like it to be green, to be carbon-free if possible. So that's kind of the goal. Well, with small modular reactors, like the NuScale design, you can do that. So one of our modules, coupled to a high-temperature steam electrolysis, will produce about 50 metric tons of hydrogen per day. So a 6-module plant could produce close to 300 metric tons of hydrogen per day, which fits very, very well with petrochemical plants, clean chemical plants. It fits that requirement exceedingly well. We can also provide processed steam up to 500 degrees C, as well as providing electrical power. So it's a very nice combination. Now, because of the level of safety that's offered by this design, which has been approved by the NRC, we can actually demonstrate that with our methodology, we can have a site boundary emergency planning zone. So we call it the EPZ. So in the US, you have to have a 10-mile radius around your plant, which is used for emergency planning. Evacuations, sirens, there's a whole types of drills and things like that that have to be done. Well, NuScale, because of our design, was able to meet all the requirements that you would meet at 10 miles, 16 kilometers out, you could meet at the fence. So we didn't take a shortcut. We met all the requirements. We were able to demonstrate that we can meet within the site boundary. So that's a big step forward as we talk to data centers and petrochemical plants, because now their facility, the end user, does not need to be within the emergency planning zone. They can be outside the planning zone. So that's a big step forward, and that was only accomplished because of our new level of safety that we offer with these very small modular designs. So it works very well with a range of different energy needs. Yeah, so I think, so you mentioned a couple of different designs, and as part of our design philosophy, we wanted to stay with a light water reactor because we know that there's a tremendous amount of data already available. So we were able to leverage about $1.5 billion worth of existing light water reactor data that was developed through the Department of Energy and through the Nuclear Regulatory Commission. So that data is already available. So we were able to leverage that. All the computer codes that needed to be benchmarked and approved, those were readily available. So we were able to make a big leap forward in a very short time because of the fact that we stuck with light water reactor technology. Existing fuel, we don't need to develop any high assay, low enriched uranium type fuels. Materials are well within the temperature range that will operate. If we want to provide higher temperature process heat, we can do that with steam heat augmentation. We've got a design that we'll be demonstrating next year. So there's in terms of compression system. So that's our philosophy has been to try to get something that's economic, that's readily available commercially, and that could be deployed very quickly, and it's well known by the regulator as well as the operators. And so we leverage not only the supply chain, but we also leverage the operating history. There's so many light water reactors around the world, over 400, and all those are a light water technology, and we learned from their experience, and we've applied that to our control room as well as to the technology itself. Oh yeah, I think you're seeing it right now. This control room is remarkable. We started off with a very strong safety case, and because of that, in the control room, we can do mostly monitoring of the systems. So the operators, there's no operator action required for any what we call design basis event. A design basis event is an event that occurs maybe once every 250 million to billion years. So they're very rare. So during normal operation, there's nothing really for the operator to do. The system is very smart, and it'll shut itself down even without the control room. So that's another step forward in terms of it distinguishes us from other technologies, including other SMR technologies. We don't need any AC or DC power for safety. So in this design, the reactors will shut themselves down in any event, and they'll remain cooled for an unlimited period of time without AC or DC power and without the need to add water. So it is really, truly a remarkable design that brings in a new level of safety. And because of that, we're able to work well with other industries where in the past nuclear could not work with. So this is a big step forward in terms of what we've done. Very big distinguishing feature. I think the fact that it's all factory built, including the containment, is another very innovative feature of our design. Significantly reduces the cost and the deployment time because it's all built in the factory. I think those are the two biggest innovations for our company. Sure, I'm excited about where nuclear power is today. What I see is a very wide acceptance, not just in the United States, but throughout the world. I think there are 70 different SMR designs being worked on all over the world, and there's a good reason for that. SMRs, and in particular our SMR design, is built for the modern grid. The grid has changed significantly, and we want to provide grid reliability, so our design provides frequency hunting. We want to provide power for desalination, for hydrogen production, for process heat. All those things are key. But I think overall, our goal is to improve the quality of life for people around the world. We want to bring light to the world. So that's our goal. And we're excited. This is a very exciting time for nuclear and very, very exciting for NuScale because of our collaborations with Entra1, a new financial model, our collaborations with our partners in Korea, Doosan, Samsung CT, and GS Energy. All these collaborations bring strength to the company, and they'll improve the quality of life for people around the world. So thank you very much for inviting me today.